Okay. Right. Divisibility. Okay, so this is where we start investigating number theory. We mentioned prime numbers and so on in the introduction to number theory. Prime numbers are, you can take as the kind of central focus of number theory in a way. Well, what are prime numbers? Prime numbers are defined as those numbers which have no factors apart from themselves or one. So before we start diving into prime numbers, we have to look at this idea of factorization of integers. Okay, so the beginning idea here is the notion of divisibility of integers. Normally, we think of division as an operation, between numbers, and you form fractions and you carry out division and you get the answer is 2.5 or something. But here we're talking about integer divisibility, and this is now a relation. It's a relationship between a pair of integers which may or may not hold. That's the way to think about it. So we think about it less as an operation, as a calculation to be carried out, and more as it's a relationship between a pair of integers, divisibility, one divides the other. It's an ordered relationship. You're saying one divides the other, and it may or may not hold for a given pair of integers. Yeah. So here's the exact formal definition. We're given a pair of integers a and b, and we say that what are we going to say? B divides a if and only if a can be written using b as a factor. So if the integer a can be written as the integer b multiplied by something else, but of course the something else has to be an integer as well. Okay, we're focused on the integers here. We're really not admitting rational numbers or real numbers into the conversation. We're just focusing on the integers. The integers are all there are, in a sense, for our view of number theory now. Okay, so if this is so, we can say that b and c are factors of a or divisors of a, or b times c is a factorization of a into integers. And also we use the word multiple, so a is a multiple of b, and it's also a multiple of c. Okay. Now, to save us saying b divides a, c divides f all the time, there's a compact notation. The compact notation is the straight line, b straight line a. If you're reading that, you don't read it as b straight line a, you read it as b divides a. And its negation, b does not divide a. Now, this causes some people trouble because they flip it around in their minds, or they interpret it incorrectly. Okay, and they'll write sentences like, if b straight line a, then b is equal to a times some other integer. But they're interpreting this as saying that a divides b. No, that's getting it backwards. This is b divides a. The symbol stands for divide, so b divides a. The order is important, isn't it? 5 divides 10. We can write 10. So if a is 10 and b is 5, 5 does divide 10, but 10 does not divide 5. You can't write 5 as 10 times something. Now you're thinking, yeah, you can, 10 times a half, but a half doesn't enter into the discussion. We're talking about integers. So you can write 10 as 5 times something, 10 is 5 times 2, but you can't write 5 as 10 times another integer. So the order is important. So if b divides a might divide b, but it might not. It's only very special cases that both directions hold. So, if you have to consider yourself, if you're the type of person who does tend to mix things like this up, then you got to come up with a strategy for fixing in your mind which meaning it has. Okay, because it's so fundamental to a lot of our discussion you really need to be able to use this fluently and not mistake it, okay? So B straight line A, B divides A. So for instance, we can write, all of these integers, 1, 3, 5, and 15, they all divide 15. So in particular, 15 can be written as multiples of all of these. 10 is not divisible by 3. You can't write 10 as multiple of 3. Note here, every integer is divisible by itself, because you can write any integer as itself times 1. And for the same reason, every integer is divisible by 1. Yeah. Straightforward. Okay. There's a bit more of a paragraph there in the notes, but so this is the definition. What it is, it's an example of a relation. It's a statement. It's a statement about A and B. It might be true, it might be false. It isn't. This doesn't stand for a value. This is another thing where where people, when they're meeting the subject for the first time, where they can make grammatical mistakes. They start writing down, like, if they write down 5 divides 10, 5 straight line 10, they write down it equals 2. No, this isn't a value. This isn't an operation which has a result. It's a statement. It's a sentence. It's a logical statement. It's something which does have a value. It's either true or false. It doesn't have the value fraction A over B or B over A or whatever. It's a logical statement which is either true or either false. And you should, when you're writing your mathematics and when you're constructing your arguments, when you're talking about number theory, you always use this notation in that way. It's a statement which is true or false. Okay? It doesn't denote a quantity. Okay. Okay. Any little questions or anything I should clarify about that? Okay. Good. Okay. Right. In common with a lot of mathematics, as soon as you introduce a new idea, you want to know what properties it has. Okay. So we've introduced this, well, we've defined this concept, this equivalent, this relation of divisibility. And it's key to the idea of a prime number. It's key to an awful lot of the number theory we'll be looking at. So we need to know everything, well, most of what there is to know about it. So straight away, we got a substantial theorem with 7 different cases. And these are all the properties, well, probably not all the properties, but all important properties of the divisibility relation, okay? And as we go through the notes, we'll constantly be referring back to these. Initially anyway, and then after a while, they'll become so familiar to us, maybe we'll start to allow ourselves some freedom and not require that we constantly refer back to these, that we just start to use them naturally. This one in particular, theorem, if you do search the PDF for the phrase theorem 2.1 part 3 or something, you'll see it comes up multiple times. And I memorize it. Normally I don't require that you memorize the theorem numbers and the part numbers, but probably if you study this course well, you'll know automatically theorem 2.1 case 3 is the divisibility of linear combinations. Very important, very key property that comes up all the time. So what are these properties? They're all properties about the relation divisibility. Reflexivity and transitivity. Reflexivity is about everything is related to itself. A divides itself for every integer A. Okay, so for every integer A divides A. Transitivity, which is nice. If you have something, an A that divides B, and also a B that divides C, the general name for this property is transitivity. The relation travels through the pair to go from the beginning one to the end one. So if A divides B and B divides C, then A will divide C. The divisibility property travels through B from A onto C. Okay? So they link up like that. You can think of it as kind of gluing the two divisibility statements together. This one has a B on the right, this one has a B on the left. You kind of mush them together, and you've got A divides C. Now, we'll be proving all of these properties shortly. I don't know if we get to all 7 today, but yeah, we'll be. seeing the proof of these, but let's just look at the statement of them. Linear combinations. Hopefully, even if I just had the titles here, you'd be able to guess what the property, what the property is. The divisibility of linear combinations. This says if you've got a particular integer a which divides two other integers. So you have an a which divides b and c. This property is saying that a divides every linear combination of b and c. Okay. So you take two integers and you form a mixture of them, meaning precisely a linear combination. So n times b plus n times c. These coefficients n and m, they are integers. Everything you see is integers with a few exceptions. All these variables are integers. So you form any linear combination of b and c, the divisibility by a is preserved. If the ingredients are divisible by a, ingredients being b and c, the result, the linear combination of b and c, is again divisible by a. Property 4, short and sweet, 1 divides everything. Properties 5 and 6, short and sweet as well, except it involves 0, which tends to throw some people. So some people remember these wrongly. It's everything divides 0. 0 divides hardly anything. 0 divides only itself. So 0 has this flipped nature. Everything divides it, but it only divides one thing, namely itself. So some people unfortunately flip this in their mind and say, oh, 0 divides everything and only 0 divides itself. That's wrong. So there's a direction to this. Every a divides 0, and if you have a statement 0 divides a, the only way that can be true is if the other thing a is also 0. Okay, we'll prove that. Lastly, and this you kind of see you're getting towards maybe something suggesting prime numbers or that. We're linking the relation to the operation of multiplication. If we have a divides b, then if you hit both parts of the statement a and b with the same multiple c, the divisibility is, well, not only preserved, but vice versa. If a product AC divides the product BC, you can, in a sense, simplify that statement, cancel the C, and conclude that A divides B. Yeah? Okay, so these are all very natural properties. If you test them out, start chucking in values for A, B, and C, and so on, you'll see that they're all true, and you'll think to yourself, well, yeah, that's obvious. If you start sticking in values for B and C and N and M, and yeah, you'll see, yeah, of course I know that. Okay, but we're dealing with this logically, mathematically. We're claiming these statements for the whole system of integers. Okay, not just the small integers that we might have an intuition about. Our brains can have an intuition about smallish integers. There's some saying, isn't it, that your brain can instantly count integers up to, collections of objects up to 7, isn't it? If you see a bunch of dots on the wall, if there's between 1 and 7, you just instantly know the number. But beyond 7, you have to actually kind of you have to actually mentally count them, I think. There's some quite deep-seated upper bound to the limit you can naturally recognize. So really, we should be careful with our intuitions. They only go so far. The integers is a very big set. It's an infinite set. There's extremely large numbers in there. You have to be careful about saying that, oh, well, this statement is obvious for integers. I'm well acquainted with integers. I know how they work. Of course, this is true for integers. Well, what if each of these integers has like more digits than there are atoms in the universe or something? They're still perfectly good integers, but you certainly can't have an intuition about them. So these properties require proof. Okay. So I would like to prove them now, or I'd like us to discuss the proofs. I might go through I don't think we well, maybe we just do a quick trip through them, because some of them are extremely straightforward. Actually, I think they're all. So let's look at the proof of theorem 2.1. Now, I purposely didn't include this in the notes. I'm not just being lazy in preparing my notes, but I think it's good practice to get a bit active and to form the things with your own hand. It helps you learn it. I think it connects it to your mind quite well when you write it down, okay, and actively engage with it. Now, what's the key ingredient? What's the key tool we're keep going to return to prove it? I should have brought my whiteboard pen, but I didn't. But the key tool is the definition of x divides y. What is it? What is that definition? X divides y, in very compact logical form. X divides y if and only if there exists z such that x divides y. So y is the multiple of x. So y is equal to x times z. Should have that on the whiteboard there so you can easily refer to it. But have that at the corner of your page. So this is the key tool. And so all of these little proofs are just going to be applying this definition. Okay, and working with this definition. So what's the first property? Reflexivity. So these are the proofs. So this has to apply to every integer. How do I prove that a divides a? Well, I want to reach a conclusion, a divides a. That's the statement here on the left with x and y being equal to a. So in order to conclude that, I can start by this. Now this says there exists a z. So in order to get the divisibility statement as a conclusion, to get this, I have to show you what the z is. So what's the z? 1. Simple and easy. So we can just observe that a equals 1 times a. You can use a multiplication sign, make it quite explicit, which implies a divides a. Oh, that's unfortunate. My 1 and divides look the same. A divides a. And the only justification we need to write is it's true by definition. This is the very definition of a dividing a, isn't it? There is an integer 1. There's an integer which fits this equation here. That's it. So you know every integer divides itself. Transitivity. Transitivity. So you've got it there in your notes. If a divides b and b divides c, then something else. Then a divides c. So it's an if-then statement. It's an implication. It's that exciting, isn't it? It's an implication. What's the most direct way to tackle an implication? Is you just take the conditions as assumptions and you try and work your way to the conclusion, don't you? So we assume that a divides b and b divides c. We give ourselves these assumptions, we make these assumptions, and now we try and reach a conclusion, a divides c. You can even, so you can start applying your little trick here of, this is the conclusion we want. I can do this. I'm a professional. I know I have an intuition about how much space I need to reach the a divides. So you be very careful when you write this on your page. You might crash and burn. You might leave yourself too little room, or you might leave yourself tons of room. But it's a good practice to do this, right? Because we know ahead of time what the conclusion we're trying to reach. If we can complete this, that's a proof of part 2. isn't it? Because these are assumptions. If we can show they lead to this conclusion, then we prove the statement. Now, how do we bridge this gap? We just repeatedly pick up our tool and try and use it. Okay. So what do we write? What's the next line we write down? Well, you look at the definition, and the definition tells you what to do. What stage are we at? The stage we're at is we've made these assumptions. What's the only way you can apply the definition to these assumptions? B is Z times A, and what you're going to say C is some other letter than Z. What's the other letter? What? Y. Brilliant. So some of the, yeah. So this implies, see, we got an equivalence here, so we'll use it as an implication. There exists two integers, Z and Y, such that B is Z times A, and C is Y times B. Isn't that right? A divides B, and B divides C. So we're forced to write that. We're forced to write that down. We've made these assumptions. The only way if you make these assumptions, that means you're starting over here. The only way to go is over there, isn't it? So I'm trying to show us trying to illustrate how we construct these proofs, because I know it's often appears kind of mystical. When you see the complete proof in the page, you think, well, how did they know to do that? So I'm trying to point out all the places where it's extremely natural what to do and where you're kind of forced to do certain things. So we make these assumptions, we get this conclusion. Now what do we write down? Yeah, so substitute, we've got these two equations now, make the appropriate substitution to reach the conclusion. And of course, how exactly, so you got this vague idea, substitute one into the other. Of course, exactly what you should do is, I mean, what leads you to A divides C? What leads you to A divides C is what would lead you to this conclusion, so I'm stepping up from the bottom here, is if you had written C as something times A, as A times something, wouldn't you? If you could write down this equation, C is A times something, then yeah, then you could conclude C divides A. Sorry, A divides C. A divides C, yeah. So what, is there something? Does there exist? This is where you're linking to the definition. Does there exist an integer that goes here? Well, yeah. Because we know C is Y times B. So I'm just repeating, really this isn't an implication, I'm just repeating myself. C is Y times B, but that in turn is Y times Z times A, just by substitution. So yes, C is something times A, the something is Y times Z. So we've got the right-hand side of the definition. Look, here's the existence of another integer, which gives you the product equal to C. So this other factor A, it does divide C. Okay? And we've proved the existence of this integer because we've assembled it out of things we knew existed, didn't we? We made this integer here as Y times Z, but we know Z and Y exist up here because we've reached a conclusion that they exist. So we're free to use them. Okay. So what we've got there is a chain of implications. But of course the things we highlight in them is the assumptions we made at the top and the conclusion we reach at the bottom. And that's exactly statement 2 in the theorem. If these two things, then this. And we've achieved it. Okay, so that's a proof of part 2. Is that okay? Any clarification on that? It works quite nicely, doesn't it? So using the definition and using just basic, I mean, if you wanted to be really formal, very picky about it, you might say you're using associativity, because you start with C as Y times B. Now really you're substituting for B, so really that object Z times A goes in as inside brackets, because it's replacing B. But then we need to shift the brackets over. So technically speaking, we're using another property of the integers, which is associativity. But associativity of the integers, it's so natural, we don't have to declare it every time. We just use it naturally. But maybe I would, at this stage, still include the justification by definition here. And then this step is by definition. When I say by definition, I mean by the appropriate definition in this context, the definition of this relation. I'm proving things about this divisibility relation. So when I say by definition, I'm referring to this tool up here, the definition of the property. Divisibility of linear combinations. I think everything after this is just kind of zips through. This is another one which needs a proof much like this. Yeah, much the same as this. Again, it's an if-then statement. So we just prove it directly. So we assume A divides B and A divides C. So you got your two ingredients, B and C. We make the assumptions about them with regard to A. And we want to form the linear combination. N and M are the coefficients. Now the statement says for every N and M. So I just introduced the variables, but the statement is about every N and M. So I just in everything you do now, you have to be sure that it works for every integer N and M. So the argument should be without prejudice about what, so this, you shouldn't go dividing by N and M because they could be 0. And of course, we're stuck in the integers here, so we don't go willy-nilly dividing things by other things, because you can only do that if the divisibility relation holds. So we've got our N and M, okay? We've got an N and M, we don't know what they are, and we've made two assumptions, that and that. It's the same first step as before. The same step that's kind of forced on us. It's just interpret your assumptions. Make your assumptions explicit. What does this straight line mean? It means there exists another integer such that one thing is a multiple of the other. So our first move here is there exists, let's call it Z1 and Z2. Stick close to the definition. There exist these two integers, Z1 and Z2, such that B is AZ1 and C is AZ2. Very natural step. You can almost do it on autopilot. You've made these assumptions. You just write in, you just rewrite. It's basically just rewriting the assumption using the other side of the definition, using the actual definition. Of course, let's do this showing off again. I want to conclude that A divides NA plus N, no, sorry, NB plus MC. That's the result I'm going for. How do you know to conclude that A divides this? You can only conclude it if you've written this as A times something. That's the only way you can conclude that A divides this thing. You have to obtain an equation like this. I'm repeating myself, I know, but Not just any old thing in here. The thing in here has to be an integer. But there's plenty of integers on the page already. You've got an n and an m, and a z1 and a z2 floating around, which we know exist. It's probably going to be some combination of those that go in here. Well, on the left-hand side, we want nb plus mc, so let's start with that up here. nb plus mc. We want to show it's equal to something. What do you do? That magic S word before, always a good thing to try and do. Solve it. Oh. Substitute. Substitute. Here's a B and there's a C, but I know what B and C are in terms of other things. So n times B is n times AZ1. And M times C, well, C is AZ2. I was far too conservative, wasn't I? Look, I've given myself a whole half a foot there, but, you know, I don't need it, because really this line now moves straight to this line, doesn't it? You've got this expression on the right, you're just factorizing it. You're just taking the A out. And what's left behind is nz1 plus mz2. Bit of a squash there. You're just factorizing this A out. Okay, this is just arithmetic on the integers. You don't need to specifically justify that. It's just basic algebra. We can do that without justification. But we should justify some of the steps. This first implication that got us started was by definition above. And this last step, which gets us to our conclusion, is again by the same definition. All the time referencing the definition of divisibility. Can you see how all the bits kind of fit together like that? And again, what have we achieved there? We assumed these conditions, and we worked with any n and z, any n and m, excuse me, and we reached this conclusion. So we showed that these two assumptions led to this conclusion. The argument talks about a pair of integers n and m, and it works for any n and m. I don't need special integers for this move to be true. It's true for every pair of integers. So we've indeed proved statement 3. We proved the implication, haven't we? Any questions about forming that proof? Okay. All right then. 1 divides everything. Okay, well, this can be quick. Why does 1 divide everything? We give ourselves an integer. We want to conclude that 1 divides A. How do you do that? You can only do that if you write A is equal to 1 times something. What's the something? A. A is always 1 times A, so 1 divides A. So that's just, it just falls out of the definition straight away, because the fact that 1 is the identity for multiplication. Everything divides 0. You give yourself any old integer A. You want to conclude that A divides 0. Well, to do that, you have to show that 0 is some multiple of A. Which multiple of A is it? 0. There is an integer that goes there. Of course, there's only one, namely A. 0. 0 is A times 0, therefore everything divides 0. 6. 0 divides only one thing. But it's phrased in this way for every A. So we let A be in Z, And it's an if-then, so we assume 0 divides A. Well, that implies that A is equal to 0 times something. 0 times Z for some integer Z. But it doesn't matter what Z is. We know what the value at the right-hand side is. What value does it have? 0. 0 times something. So A is 0. The only thing that's divisible by 0 is itself. Seven. Okay. So you let A, B, and C be integers, with C being non-zero. That's an if and only if. So to prove an if and only if, you want to assemble a chain of if and only ifs. We start off with one side of the result. We try and move to the other side. Well, this means there exists a Z, an integer Z, such that BC is equal to AC times Z. Now, what's that equivalent to? Well, you just cancel the Z. So cancel the C from both sides of that equation. That equation can only be true if B is equal to AZ. But notice, and that's important. You can only remove the C and conclude that B is A times Z as long as you know C is non-zero, okay? Because if C is 0, this equation is true no matter what B and A and Z are. If you've got 0 in the middle on both sides, you've got 0 on both sides, no matter what the other values B, A, and Z are. So you certainly couldn't automatically conclude B is equal to AZ. That's only true for very special B, A, and Z. Not true for every B, A, and Z. So the C is important there. It's used as you go from here to here. It's important for that step. And of course, what we have there is just the very definition of A dividing B. The fact that there exists some other integer Z and B is equal to A times Z. Okay. So that's properties 1 through 7 of divisibility. I think I probably spent longer than that I did the previous 2 years, because it seems to have practically filled out the whole lecture. But I think it's no harm, because it's a very nice first set of proofs to see. We've introduced a new definition, and we show how we work with it, how we use it. The proofs in the course get more complicated, right? But what you want to try, don't just dismiss these early ones. What you want to try and pick up for them is the way of thinking about it. You know, the day started, the hour started by where we introduced this new piece of notation, this relation, A divides B. We proved a bunch of properties of it. We kept going back to the definition, just working the definition all the time to extract the properties. That broad approach is really what's going on all the time when we're proving things in this course, okay? Or it's a very common theme. So often when you're in the middle of a proof or you're wondering where to go, often the thing that gets you started is think, okay, well, what definitions are there involved here? What's the actual meaning of the definitions? How do I work them? How do I bring in the objects they talk about? How do I make my way to the definition statements for the conclusions and so on, okay? And this trick of knowing where you're trying to get to and trying to bridge the gap, that's a very useful way to approach these things as well. And it'll work for us in more complicated situations as well, okay? I'll scan these pages up. I'll attach them to the recording there as comments. And, well, I think we'll just leave it there for now. We'll continue with this on next week. So I've got you for 2 lectures next week. Me and Andy just swapped around this Thursday and Friday. So I'll see you for 2 lectures next week, and we'll get stuck into this divisibility chapter.